So until this point, we have graphed our basic displacement values on a graph, right? Move forward, move backward, move up, move down, all that kind of stuff. We've shown that on a graph. But now we're going to talk about complex motion on a graph. So this might be where an object moves forward, then it stops, then it moves backwards, and it does all of these things in one kind of trip, okay? So if you have complex motion, it needs to have a graphical representation. We've so far looked at what's called motion diagrams, where we just draw a really basic picture of it moving forward or backwards, but now we're going to put it on a graph called a displacement versus time graph. Okay, a displacement versus time graph. Now, in the first semester, we did a whole bunch of units on graphing and drawing correct graphs and writing correct graphs, all that kind of stuff. I want you to think back to that when we did all of that practice with graphing. Tell me, what are 3 things a graph needs? 3 things that a correct graph has to have. Okay, origin is just part of the graph. What does it have to have? What do you have to put on it? Has to have an independent variable and a dependent variable. It's got to have the correct labels on our graph. Okay, it has to have the correct labels. And so if I'm going to draw a graph here, if I'm going to draw a graph, okay, or even a graph that looks like this, where does my independent variable go and where does my dependent variable go?
Dependence on the y, independence on the x.
What'd you say? Dependent is on the y and independent is on the x axis. Okay, the thing you are controlling, the thing you are the thing you have at regular intervals is on the x axis, and the thing that you are measuring, the dependent variable, that goes on the y axis. Okay? If you're looking at the title of a graph, this is the y-axis versus the x-axis, right? Whatever is listed first is usually going to go on the y-axis. So displacement versus time. Time goes on the x-axis and displacement is on the y-axis. So it looks something like this. Okay, I need to have a label here on this. Oops. I need to have a label here on this y-axis. So why don't you go ahead and add that to here. This would be, oh my goodness. This would be displacement. And not only do we need the label on the axis, but we need to have the unit. So we would label it with meters there, okay? And time might be measured in seconds. All right, so 3 things that a correct graph needs. We need x and y labels. We need axes labels. What else do we need? Okay, it's not called a header, but that's close. A title. It needs a title. Needs a title. Okay, a title. It needs axis labels. And what's the last thing? Do you remember? We outlined 3 main things.
Correct information.
No, okay. These are axes labels. That's what those are. Those are axes labels. A title would go up here. Displacement versus time. What's the last thing we need when we draw a graph?
What's it start with?
A C.
I don't know.
I know. The last thing we need when we draw a graph is a correct scale. A correct scale. And so a correct scale means that when we draw a graph, just listen. When we draw a graph, we don't want all of our data points up here at the beginning. Right? We don't want the graph to be like that. And then all of this empty space over here. We want our graph to be scaled correctly so that our scale takes up, or our graph takes up, most of our visible space, right? We want the graph to be zoomed in enough that we can actually see what's happening with the data, all right? When we draw a graph, when we are able to draw a graph from start to finish, we don't want to crowd all of our data up here in this section of the graph. We want to make sure that it's spread out and zoomed in. Does that kind of make sense? Yeah. All right, so we need title, axes labels, correct scale. Those are 3 things that we got to have, okay? So let's keep moving here with displacement versus time graphs. What this graph is showing me is that when my time started, right, when time equals 0, my object was at its starting point, was at a displacement of 0 meters. After 1 second had gone by, how far ahead was my object? How many meters had it moved?
3. Or 1 meter.
No, where is it at? Read the y-axis. At 1 second, here's my graph. I had gone 2 meters. After 2 seconds, how far have they gone?
4.
4 meters. Can everybody see that?
Yeah.
We need to make sure that we feel comfortable being able to read that graph, right? That's what it is, right? We have to be able to look at the graph and say, after 2.5 seconds, what's my displacement? 5, right? I'm going to come find the graph at that intersection and say it has moved 5 meters, right? At 2.5 seconds, it has moved 5 meters. Are we okay with reading that?
Yeah.
Okay. All right, so let's look at our displacement versus time graph. It shows us that relationship. When we look at a displacement versus time graph, the slope of the line tells us, if we calculate the slope of the line, it tells us the object's velocity. It tells us the object's velocity. So let me look at this graph one more time. Okay? I want to pull up this graph one more time. All right? If I have a displacement versus time graph, and I have an object that's doing that. All right, we said that displacement is on the y-axis and time is on the x-axis. If we were to calculate the slope of the line, that would be the same as calculating the object's velocity. Okay? Because tell me, what's the basic equation for slope? What's the equation for slope? How do I calculate the slope of a straight line? No, that's the equation of the whole line. Okay, if I'm talking about the formula for a line, y equals mx plus b. M is the slope. How do I calculate the slope of a line? Yes, good. y2 minus y1 over x2 minus x1. Another way to say it is rise over run. Have you heard that term before? To calculate slope, we do rise over run? Yes or no?
Yes.
Okay. Do we feel comfortable calculating that? The change in y over the change in x. Give me a yes or no. Okay. So if we look at our graph here and we say we're looking at the change in the y-axis over the change in the x-axis, that's the same as looking at the change in displacement over the change in time. And what equation does that look like? What equation does that look like? The equation for velocity, right? Doesn't velocity equal displacement over time?
Yes.
Okay, do we see the connection between slope and velocity here? Change in the y-axis, which is displacement, over change in the x-axis, which is time. Okay? So how do I calculate the slope of a line, right? We're looking at rise over run. Okay? Or you could say y2 minus y1 over x2 minus x1. Is that the equation that your math teacher gives you to calculate slope?
Yeah.
y2 minus y1 over x2 minus x1. Okay, slope. No, you can do it. It'll be okay. We'll get there.
At least she's not making us into point slope form.
You don't have to do anything with point slope form. That's right.
Honestly, I like point slope form. Okay.
All right. What would it mean on a graph to have a negative slope?
Right to go the other way. Right to go like west.
Going in the
So let's say that our graph looked like this. Displacement over time, and my object
go back.
had a slope that looked like that. It means we are going backwards or downward, whatever way your object is moving, backwards or downward. So it doesn't mean we're moving so slow we're going negative velocity, right? It just means that we're moving in the backward direction. Okay, because we know that negative velocity doesn't mean we're moving slower than 0, right? There's no way we can do that. Negative velocity means that we are moving in the backward direction, so west or south. All right. Constant velocity. So let's calculate, what is this person's velocity? Okay, what is this person's velocity? So if I want to calculate the slope of a straight line, I get to pick any 2 points, don't I? Yes or no?
Yeah.
I get to pick any 2 points. If it were me, I'm going to pick one of my points as 0, 0. Right? Because that's really easy to calculate with 0. Don't we agree? Mm-hmm. The second point could be anything I want. I'm going to pick this one in the middle. Okay? Because it has whole numbers. Okay, so I like that. So the coordinates for my second point are what? What's the coordinates of this point right here? 2, 4. Right? My x is 2, my y is 4. What is the point? What's the coordinates of my first point? 0, 0. So now when I go to calculate the slope of this line, we said our slope formula is rise over run, or we can calculate it with y2 minus y1 over x2 minus x1. All right, so I'm going to just come pick out my coordinates here. y2, right? If this is point number 2 and this is point number 1, my y component comes second. So it would be 4 minus 0, right? 4 minus 0 over x, x2 minus x1, right? y2 minus y1 over x2 minus x1. And so that means I have a slope of 2 over 4. And so when I reduce that down, what's it tell me? 2. My slope is 2. And how would I label my slope? What would my units be if this is meters and this is seconds? It would be meters per second. Just like we write out the unit for regular velocity, right? Meters per second. All right, here we go. What does a horizontal line mean on a displacement versus time graph? So, for example, from 7 to 12 seconds. So, my object from here to here, what's it doing? Yeah. It is not moving. It is not moving. Is their displacement changing at all during that time interval? No. So, that means it is standing still.
Is that also called plateauing?
I don't know. I don't know about it in math. Okay, tell me what would be happening. I want to start looking at some of the relationships of what's happening in the motion here. So let's just walk through this time interval by time interval. So from 0 to 2 seconds, what's my person doing?
Nothing.
Let's assume this is a person walking. So from 0 to 2 seconds, what are they doing? They're just standing still. They are not doing anything. From 2 to 5 seconds, what are they doing? Walking backwards. They are moving backwards. How do I know they're moving backwards? This is the positive direction and this is the negative direction, right? So my slope is going in the negative direction. I am moving backwards. Okay, from 5 to 7 seconds, what am I doing? I'm going forward. And what do you think it means that I cross the x-axis here? What's that mean I did?
Ran.
No?
Oh, you went back to your start.
That's right. I passed my starting point. Okay, so if I'm this person, right, and here's the origin, I stand here for 2 seconds, right? I walk, I'll call this backwards, right? I walk backwards for a little while, and then I walk forwards. Right, and I passed my starting point. Okay? At 5 to 7 seconds, I'm still standing right here. What am I going to do for those 5 seconds?
Nothing.
I'm going to stand still. Then what am I going to do? And I'm going to go backwards. Am I going to go backwards really slowly or really quickly?
Quick, because it's going like stupid.
That's right. I'm going to walk really quickly backwards because I can tell that my slope is really steep. Right? This steep slope means I cover a lot of distance in a short amount of time. That would mean I'm moving quickly. Would we agree with that?
Yeah.
So from comparing these this time walking and this time walking, which is faster? The first or the second? Yep, the second backwards trip is faster than the first, right? We could calculate the slopes and you would see that, but just looking at the slope of the line tells us he's walking faster. Okay, so from here to here, what am I doing? I'm walking forward, right? I'm walking in the forward direction. I'm still on the negative side of my starting point, but I'm still walking forward, right? Positive slope means positive velocity. Then from, 16 to 18, what am I doing? Standing still. What am I doing from here to here? I'm walking forward and I happen to end up exactly where I started, right? That's not always the case for these motion graphs, but I'm ending up exactly where I started. Okay? Tell me what questions do we have about kind of walking through what happened with that graph. All right, I'm going to add on some questions here. Tell me, what is the velocity from 12 to 14 seconds? Let's do this one together. What is the velocity from 12 to 14 seconds? Okay, this is point number 1. This is point number 2. Okay, we can calculate it as rise over run. So the change in y minus the change in x. So what's my final y? Actually, let's just go with, what's the coordinates of my second point? What's the coordinates of my second point right there?
-6.
Well, which one comes first? 14 comes first. The x component comes first. So 14, then what? -6. What are the components of my first point? 12, 10, 11, 12. 12, then what? 2. Okay, if I'm going to calculate the slope on that, I'm going to do y2 minus y1. Okay, so -6 minus 2 over x2 minus x1, so 14 minus 12. So that gives me a velocity or a slope of -8 over 2. And so how do I reduce that? What's my answer after I reduce it? -4 meters per second. Does it make sense to us that their slope is coming out negative?
Yes.
Does it match what we predicted?
Yes.
Right? Because our slope is literally a negative slope, right? Our slope is pointing us downward, so we're going to have a negative slope there. Okay, do we agree so far? All right, I want you to try this one on your own. I want you to calculate the slope or calculate the velocity from 5 to 7 seconds. Okay, so 5 to 7 seconds is here to here. Okay, so I know on your chart, is it a little small? Okay, so you can see up here what points you need to calculate our velocity. Okay, remember, when we say what is the velocity, that means we are calculating slope. We need to start correlating those two things. Any other questions with calculating slope? Okay. I want you to look at, let's walk through again what's happening in this graph. So from 0 to 1 second, what's happening here? Standing still. From 1 to 3 seconds, they are rocking forward. From 3 to 4.5 seconds, they are standing still. And then from 4.5 to 6, they are walking backward. All right, so you can write that out on your sheet if you want to, but you don't have to. This graph, I think it's a little easier to see the rise over run, okay? Because on this graph, you'll see for every second that goes by, right? 1 second goes by, they went up 20 over 1, right? Up 20 over 1. So my slope here is 20 meters per second, right? I went from 20 to 40, so that's up 20 meters over 1 second. Up 20 over 1 second, okay? For here, it's a little tougher to see, but if I'm going to go down 20 over, I don't quite get there, right? So we've got to calculate that one a little bit differently. But for this one, where it crosses through those intersections, nice, it's easy to calculate that rise over run, okay? All right, what's the velocity of our object from 1 to 3 seconds? Well, we just calculated that, but let's go ahead and write it out, right? If I were to look at the velocity from 1 to 3 seconds, that's this interval right here, 1 to 3, okay? And we already said from 1, we're going up 20 over 1. So my velocity has to be 20 meters per second. Okay? Now, what if I was going to ask you, what is the velocity of the object from 3 to 4.5 seconds?
0.
It has to be 0. It has to be 0, right? Because we already said we are standing still. So my velocity when I'm not moving, my displacement is not changing. It has to be 0 meters per second. Okay, it has to be 0 meters per second. All right. Tell me what's happening in part A here.
Walking forward.
We are walking forward. Tell me in part B, what are we doing?
Standing still.
Standing still. And then in part C, what are we doing? Walking backward. Now, tell me, which part of my graph, A, B, or C, has the greatest velocity? Which part of my graph are they moving the fastest? A. Has to be A. And so why do you know? Just by looking at it, how can you tell that during part A is moving the fastest? Jacob? It's a steeper slope. Good. What if I asked you at what part of my graph are they moving the slowest? What would you say?
B.
It has to be B, right? Because what are they doing at part B? They're not moving at all, right? So there's nothing could be slower than 0. Okay, so part B would be our slowest moving part there. All right. Describe the motion in words given the following. So for each segment, mention the starting position, direction of motion, and rate of motion. So you're going to do this one on your own. You're going to say from 0 to 2 seconds, they're moving at this velocity, right? You're going to calculate that. You're going to say from 3 to 4, they're doing this, and from 4 to 7, they're doing this. So you're going to have 3 different time intervals you have written out, okay? So I'm going to give you this on your own. I want you to try this here in a couple minutes. You're going to describe from 0 to 2 seconds, they are moving in the whatever direction with this velocity. So you're going to give calculated values there as well. So I'm going to give you a few minutes to do this one on your own. So from 0 to 2 seconds, we're moving forward at a constant velocity. I know it's a constant velocity because my line is straight. Okay? I'm moving backwards here at a constant velocity. If I had a velocity that was not constant, we're going to dive into that a little bit more tomorrow, but my line might look something like that. Right? It might be a curved line. That would tell me that my object is speeding up or slowing down. Right? It's not just moving at a constant speed, then stop. It would be speeding up or slowing down. That's not a line we will have to ever calculate. It's just something that I like us to be able to be aware of what it's doing on the graph. It's good for us to know that. Okay? All right, last one I want to look at today is a comparison of 2 objects in motion. Consider the position versus time graph at your left for cyclists A and B. Do the cyclists start at the same point? If not, which is ahead? And at t equals 7 seconds, which cyclist is ahead? And how do you know? So I'm going to give you about 2 minutes. 2 minutes to answer those questions on your own, and then we'll come back together and figure out if we agree or disagree. So everybody is doing this work on your own for about 2 minutes, and then we're going to come together. So I want everyone to have answers for those questions. So let's figure out, do the cyclists start at the same point? Say it together. What do you think? Yes or no? No. How do we know that they don't start at the same point? Are their y-intercepts the same? Right? Because their starting point is here, right? T equals 0. And so my starting points are not the same, right? My y-intercepts of those lines are not the same. So my starting points are not the same. So how do you know? Well, I know because their y-intercepts are different, right? Their starting points are different on the axes. Which of them is starting out ahead of the other? B is starting out ahead, right? This red line is line B. And I'll make it green, this green line is A. So at 7 seconds, which cyclist is ahead, right? I'd probably put 7 seconds somewhere around there. Okay, so which cyclist is ahead at 7 seconds? Which one? What do you think, Cora? A. How do we know it? Yeah, A's displacement, right? If I go look at the displacement of A compared to the displacement of B, right? A's displacement is greater. So A is farther ahead at that point. If I asked you, at what time are the cyclists at the same point, what would you say? 5 seconds, right? Because that's where the lines intersect. All right, are we feeling good about being able to analyze graphs like this? Yes? No? Can you read what this graph is saying and answer questions? All right, very good.